Explosions don't power cars. It's liquid and gas.
Do you have a blockage? Because I'm 76% sure that there's something called combustion energy, which means there's an explosion in the engine that pushes the car forward.
If that's how it worked, we'd all be dead.
What about rockets? That's gotta be proof.
Was that the sound of a misinformed discussion?
No. Rockets are powered by something else. The explosion is just special effects. What are you looking at?
Who the heck is this nerd?
I'm the MMB, prepared to be corrected.
What's he staring at?
What? Should we inform someone that Kook has escaped the room?
Oh. Right, we don't have the budget for an intro yet. Guess we'll just have to do it the old-fashioned way.
What just happened?
Where are we? How'd we get you? Who are you?
I already told you, I'm the MMB, and don't worry about how we teleported.
Don't worry, we bloody teleported.
I said don't worry about it.
Still haven't answered where we are.
Oh, I don't know exactly where we are. I just teleported us to the nearest highway.
Why?
Because you were horribly incorrect in your earlier argument, and I had to inform you so.
About what?
About combustion energy, of course. It's really a marvel that it works. The chemistry behind it is amazing.
I'm never wrong, and I know I'm not wrong about this.
Alright then. Tell me, kid, what is combustion energy?
My name's not Kid.
Oh. You're right, I never did ask for your names, huh?
Oh, Jimmy Romano and Brett Anderson.
Don't give him our names, idiot.
Well, regardless, nice to meet the both of you. Anyways, Jamie, you were telling me about combustion energy.
Well, yeah, basically there's an explosion in the engine that pushes the car forward.
You're partially right. Starting with gas, we do burn fuels to produce energy, commonly gas, which is a hydrocarbon, meaning that its molecules are made up of carbon and hydrogen atoms. As gas is burned, it creates large quantities of energy and a waste product of carbon dioxide and water vapor. This is the chemical reaction that produces the energy for your engine.
Yeah, Jamie, you're way off compared to this crazy guy.
Brett, he's a crazy guy.
He can't teleport.
Shut up, Brett.
Thank you, Brett. Anyways, to continue with my explanation, gas's main component is octane, whose chemical formula is C8H18. The balanced chemical reaction for octane burning is this. As octane burns, it releases 44,400 joules of energy for every gram of it that's burned. This is the energy that propels your car forward.
And we know this is correct information. How exactly?
Well, I mean, I trust it. You can't teleport after all.
Well, my sources will pop up here when I give information. For example, watch what happens after I tell you that cars utilize the energy created from combustion to fire the pistons in your engine, allowing it to accelerate. It's this continuous chain reaction of chemical reactions that allows your car to move in any direction that it wants. To deem it an explosion is just a disrespectful oversimplification, in my opinion. See?
How'd you do that?
Same way I teleport.
Can you teach me?
Yes, I can teach you about how combustion energy isn't just used in cars, but also in coal-based power plants. Let's go!
Skills. I hate you. Both of you.
You don't gotta like me, you've just gotta learn.
Where are we anyway?
Oh, we're in a coal-based power plant.
And you know this how?
Because he said that right before teleporting.
Brett's right. This is a coal-based power plant. In America, the coal industry is crucial for its power supply. Last year, according to the Washington Post, coal accounted for 30% of the entire power grid. While it is being phased out by more modern methods, coal is still crucial in some regions, like in West Virginia. There, coal supplies 94% of its entire power grid. But aside from all of that, power plants like this one are a great example of combustion energy because the very source of the electricity is the energy released from coal burning.
I knew it. I like them apples.
You didn't know any of that.
You did too. I was a coal miner.
That explains a lot, actually.
Yeah, it does. Coal is the primary source of 19 states and second in another 9.
The Washington Post confirms that as well. I'm impressed, Brett.
Thank you, but I still don't know why it's so popular.
Well, hold it.
Thank you. Just want to be reminded what silence sounded like. Please get this over with.
Anyways, to understand why coal is so commonly used, you'll need to understand what coal is first. Coal can be defined as a combustible sedimentary rock. It was formed from decomposing plant matter that was essentially pressure cooked for millions of years underneath the surface of the earth. There are 4 main classifications of coal: anthracite, bituminous, subbituminous, and lignite. The 4 classifications describe the developmental stages of coal, with all of them being especially susceptible to combustion. This is mainly due to their high carbon count. To help you visualize it, I'll show you their empirical formulas. This is high-grade anthracite, and this is bituminous. Notice the high carbon counts.
Wow, that's cool.
Shut up. You didn't know a word of that.
Doesn't mean I don't think it's cool.
Well, the way that it works, in layman's terms, is that coal-based power plants produce electricity by burning coal in a furnace, which heats up a boiler, producing steam which flows into a turbine, which is connected to a copper coil generator. The steam is then cooled, condensed, and returned back to the boiler for the process to start back over again. Cool, are we done here? Yeah, I think that's enough combustion for today.
So what next?
Next, we go home.
So no more learning?
Oh, well, there's always more to learn, Brett. Is there any questions that I might be able to answer for you?
Yeah, so if 30% of all our power comes from coal, where's the other 70 come from?
That is an excellent question, and it's a wide variety of renewable and non-renewable energy sources, ranging all the way from nuclear over to geothermal.
Nukes? Like the bomb nukes? That's awesome!
Well, while that was the origin of the method, it's not exactly quite that simple. Here, I'll show you.
No, you don't.
Let's go!
Where's my jacket?
Well, the teleportation, it can result in some things becoming lost. Just be happy it wasn't a body part.
So where'd you teleport us this time?
This time, it should be a nuclear testing facility.
A what?
A nuclear test site. What's the confusion?
Aren't we gonna get, like, radiation poisoning or, I don't know, a cancerous mutation?
First of all, that is not how it works at all. And secondly, no, I made sure to teleport us a few decades ago, right before the test actually occurs, so no harmful radiation.
You can time travel?
I can!
Lucky!
I know, right? Anyways, history lesson. Did you know that nuclear power was first driven through the development of the nuclear bomb during the Second World War? After the war was over, research and development shifted towards naval propulsion, which then, in 1956, shifted once again to the nuclear power that we know and love today.
I actually knew most of that.
Okay.
I did. It still doesn't say why we're here now.
Oh. Well, this was one of the first test sites that pioneered the way for nuclear power.
Wait. This is gonna be a test site?
Yes. Hey, you guys should know. Cool guys don't look at explosions.
Get us out of here now.
Fine.
So, where'd you bring us?
Chernobyl, Ukraine.
Are you trying to bloody kill us?
Oh, Brett, would you calm down? He's not trying to kill us. Right?
Of course not, Brett. We're here to study nuclear fission, not death.
Wait. That's called nuclear fusion.
Incorrect. While nuclear fusion is a thing, there are substantial differences between it and nuclear fission. Nuclear fission is a reaction in which a heavy nucleus, meaning that it's radioactive, is bombarded with neutrons and thus becomes unstable. This unstable heavy nucleus then degrades, decomposes into 2 nuclei of equal size and mass, resulting in an enormous, powerful release of energy and the release of 2 or 3 more neutrons. These neutrons then go on to interact with more heavy nuclei that cause even more emissions and more fissions, which cause more energy and more neutrons to be released, and so on and so forth. This multiplying effect is known as a chain reaction. And this reaction is so quick and so energetic that in just a fraction of a second, it can produce 1,000,000 times more energy than that which you would get from burning a block of coal or detonating a stick of dynamite of the same mass. And not to mention that this is all happening at a speed greater than a chemical reaction.
And how is this supposed to produce electricity?
Oh, I don't know.
Wow. That's surprising.
I'm joking. Of course I know. I'm the MMB. I wouldn't be the MMB if I didn't know.
What's an MMB?
Get back to me on that.
Okay, anyways, continue.
Better idea. Bring us home.
I think I'll stick with Brett's idea. Nuclear power plants work in the same manner as pretty much any other power plant, through the use of steam and turbines. A nuclear power plant utilizes the heat created from a nuclear reaction to boil water, producing steam which flows with great pressure into a turbine, creating electricity. With the only main difference being what I mentioned earlier, the nuclear reaction, the controlled degradation and chain reaction of uranium atoms interacting with stray neutrons, whose chemical formula, by the way, is this. And just a fun tidbit, if the reaction weren't controlled and there was just a teensy tiny bit more loose uranium, the reaction would be a lot more violent.
So, the explosion we saw at the test site, that was an excess of uranium?
That's right, Brett. Now you're getting the hang of it.
Okay, I'm going to regret this, but is nuclear power more popular than like coal or anything else?
Jamie, I'm so glad to see you're joining in on the fun. And to answer your question, nuclear power last year accounted for about 20% of America's power supply. And currently, there are 61 operational nuclear power plants in America today.
Okay, so it sounds like a very efficient form of power.
It is very powerful, but it's dangerous and produces chemical waste. The International Atomic Energy Agency, or IAEA, estimated that about 370,000 tons of heavy metal in the form of used energy, used fuel, have been produced since the first nuclear power plant was put into use.
Back up. Chemical what?
Chemical waste.
I heard him.
Then why'd you ask what it was?
Just be quiet and let the crazy man speak.
The waste can't be destroyed. It can only be stored. The US has a few waste drop-off sites, but some have been around for a long time and are beginning to degrade, thus risking the safety of the environment around it. This is the most likely cause of problems stemming from nuclear fission, with of course the more flashy ones being what happens when a nuclear power plant isn't properly maintained.
Oh, what happens?
You do know what happened in Chernobyl, right?
No.
Of course you don't, dolt.
Oh, well, do you?
Well, yeah. Russia was testing their nukes on the city and boom, Chernobyl.
No, that is not at all what happened. The 1986 Chernobyl travesty was the meltdown of the power plant's fourth reactor, Chernobyl 4. This was a product of an antiquated Soviet-era design and human error. The workers ran the plant at unstably low power levels, without adjusting the other systems accordingly. The fatal flaw was the cooling levels not being within the right range, which led to there being a power surge, which led to there to being a surge in heat, which led to a violent meltdown.
What?
The place was properly kept and broke down. Just turn around and see.
Not cool.
Not cool at all, Brett.
Okay, so are there other sources of power? Because nuclear and combustion, that's not a good situation how I want to.
No, you're right, it's not. There are plenty of other sources, such as geothermal. It's great. It's clean, it's reliable, it's renewable, and it's very efficient.
Ooh, that sounds cool. Can we see that next?
Or, and hear me out here, we could go home.
Of course, Brett. I'll teleport us right there.
Fine.
Yeah. That's another adverse effect of the teleportation. Just, give your stomach a moment to settle and you should be fine.
Jamie, hold it in. Be a man.
Oh.
Where are we?
This is glorious Iceland.
Why are we in Iceland?
Because Iceland is one of the top users of geothermal energy, currently standing with 89% of their homes being powered or heated via geothermal methods.
That's pretty cool.
I know.
Yeah, so cool.
Anyways, so why aren't more countries like Iceland since it's such a reliable source of energy?
Well, geothermal energy is actually rather rare. The natural hot springs, geysers, or other such formations aren't as available as they need to be for it to be a more universal source.
So it's not as reliable because it might die out soon?
No, that's not what I meant. Geothermal energy is very reliable in the sense of its lifespan. Keep in mind that these formations were formed millions of years ago by the Earth itself, and thus show no signs of dying out anytime soon. What I meant earlier is that the methods aren't as, of course, like I said, aren't as commonplace as they need to be, but these pockets normally aren't as large as they need to be to support large commercial use. They can be large enough for a small home, but anything bigger would just be impractical. But the methods, the mechanisms are actually very reliable. It can last up to 20 years when properly maintained. And then after that, replacement and repair is pretty intuitive.
So I'm confused. So if it's so reliable of a source, and it's so easy to maintain, why aren't more people using it?
I understand, it is very confusing. While the method is pretty straightforward, the actual mechanism is tricky and often expensive, though the investment turnover rate is actually pretty quick, normally 2 to 10 years. But the main reason for the high cost is the holes that need to be bored into the ground. For homes, it's rather small, typically only 8 feet. But for anything larger, say an apartment building or an office space, you're going to be looking at a hole that is at least a mile deep into the ground.
Yeah, that's a bit much.
Anyway, it's 2:15. We gotta go home soon.
Jamie, chill out. He's the MMB. He's got this.
Yes, Jamie, no need to fret. I'm well aware of your schedule and you'll be home in time for practice.
How did you know I had practice?
I'm the MMB. Duh.
And I still don't know what that means.
And you don't need to know.
Anyways, can we go see the power plant now?
Oh, power plant. Excellent idea, Jamie.
Or, there's no use in going home, is there?
That is the one thing you've been correct on today, Jamie. Congratulations. This is a geothermal power plant in California. Currently, the US is #1 in the usage of geothermal energy, even though the industry's contribution to the power supply is only 0.4%.
Wait, how can the US be #1 with 0.4%? You just told us Iceland was 89%.
That is true, but keep in mind that that percentage is only representative of Iceland's residential power grid, not its total. Also keep in mind the difference in size between the power grids of America and the power grids of Iceland. The American power grid is unimaginably large, and so a number like 0.4% may sound small, but just think of how much it could possibly represent, and how much it does represent.
Yeah, I guess that makes sense. But how does it work?
Well, there are 3 main ways of converting energy: flash steam, dry steam, and the binary cycle, with the common denominator of all 3 being the use of steam turbines.
Alright, is it just me or do all these different types of energy just use steam?
Yes, that is the common denominator. Good observation, Brett. And let me tell you why. These turbines all have fins,
This is so boring.
boring.
Yes, it's just a bunch of stuff that all results in steam pushing a turbine.
Boring. This is boring. Will it be boring when we run out of fossil fuels? Will it be boring when we all die from carbon dioxide poisoning? Oh yes, it's all of course fun to deal with flashy, fun nuclear explosions and nuclear chemical reactions and all that stuff. But as soon as I try and bring up a clean, renewable, reliable source of energy, it's suddenly boring.
Don't get ahead of yourself. You still haven't brought up something like solar energy, and you were boring before this. And you're the one who kidnapped us and brought us around, teleporting us to these random dangerous sites and almost getting us killed.
Yeah, you're right. I did neglect to inform you guys about solar energy, didn't I? Let's go.
Oh wow, it's bright.
Let me guess. Solar plant?
Not just any solar power plant, the largest in the world.
Wow.
Yeah, the Nor Complex Solar Power Plant is the largest in the world and will provide power for over 1 million people when completed in 2020. It has a 580 megawatt capacity and has already reduced the carbon emissions of Morocco by hundreds of thousands of tons since it was first activated in 2016. Did I mention it was built in Morocco?
Yes, you did mention that.
Anyways, somebody who I think might be able to explain solar power better than I can, hopefully not better, is my friend Dr. Alexander Edmund Becquell. Here, let me bring him in for you.
Wait, take the hint. Bring me home.
Fine. Brett, would you like to go home as well?
Nah, I think I'm gonna stay and listen.
Oh, well, I'm glad to hear. Jamie, I will teleport you out and bring in Dr. Edmund.
Hello, MMB. Long time no see.
Hello, Doctor. Nice to see you again. Hopefully you have, Remembered your lesson since last time?
Of course, never overshadow the MMB.
Oh, Doctor.
What's the MMB stand for?
He'll tell you much later.
Thank you. And just before the doctor starts, let me give a brief explanation. So Dr. Edmund Becquerel first discovered solar energy in 1839. I have since suspended him in time so he can observe the progress of his discussion in real time, making him the world's most foremost expert on solar energy.
Thank you for the acknowledgement. I've actually prepared a short discourse to share with you. So, I was conducting an experiment on the properties of selenium and discovered that it's capable of actually producing an electrical current when exposed to light. This experiment was later actually repeated by a scientist named William Gris, who published a paper describing the action of light on selenium. This idea was further developed by Charles Fritz, who came up with the idea of producing electricity from sunlight and developed the first commercially viable solar panel capable of creating a continuous constant electrical force from not only direct but diffused sunlight.
If I could add a word.
However, these types of solar panels were very primitive, inefficient, especially compared to the other main sources of energy at the time, namely coal-fired and oil-fired power plants. Much later, this solar module design that is used in production of modern commercial solar panels was created by Russell Old and first used by Bell Labs to create what we know now as the solar panel. Now to describe the chemistry of solar energy. A solar cell captures light from the sun and converts the ultraviolet, visible, and infrared waves into usable electrical current.
That's a lot of information.
There's more. The active surface of a silicon cell, which is made from a material known as silicon. Silicon is a semiconductor, which means it allows electricity to pass through it at a specified rate, which is dependent on temperature and pressure. The semiconductor properties of silicon are the perfect environment for reactions that allow solar cells to capture energy from the sun as a constant electrical charge.
Yes. Thank you, Doctor, for that very descriptive introduction. Why don't
I'm
I
not
take...
finished yet. Solar cells are composed of 3 layers. The first is 99% silicon and a few percent phosphorus, which contains more electrons than silicon. This disproportionate negative polarity between the two elements creates an excess of electrons that are free to move around the atomic structure, therefore increasing its conductivity. The bottom layer of the wafer contains silicon and an atom that contains fewer electrons, such as boron. The disproportionate positive polarity between these two elements limits the number of free electrons that are able to move within the atomic structure, decreasing its conductivity. When an electron is missing from its normal position, the molecular structure gains what's called an effective positive charge.
Ah, yes, thank you. I'm sure I can take it from here.
Let me continue. The bottom layer contains a deficit of electrons, which is why it's called a positive type or p-type layer, as it favors the collection and transport of positive charges. The top layer is called the n-type or negative layer, as it favors the collection and transport of electrons. The thick middle layer has only a marginal decrease in electrons compared to pure silicon, making it slightly p-type. Thin lines of manganese silver or a type of silver alloy are printed on the surface of the n-type layer. And the p-type layer is coated in a solid sheet of aluminum.
Thank you. Doctor, please, if you don't stop interrupting me.
One or two more things here. When light waves contact the surface of a solar module, only the wavelengths between 350 and 1,140 nanometers are absorbed by the cell. This is one reason why solar power plants require such large concentrations of thousands of commercially standardized solar cells, since only a percentage of the entire visible, ultraviolet, and infrared spectrum are able to pass through a single module and participate in the energy conversion. When a ray of light hits within the specified range and reaches the middle layer, the photon causes an electron to separate from the atom of silicon and moves freely towards the top layer, which readily accepts negatively charged particles. The remaining broken positive charge conductor then migrates to the top layer, which readily accepts positive charged particles.
That's a lot of sciencey stuff, Doctor, but I enjoyed it.
And it's not over yet. Now that the electrons in positive charge conductors have effectively separated themselves, by conducting conductive wires to the silver and aluminum plates, you can provide these electrons and positive particles the needed route of transport, which allows them to charge the receiving device, then return to the bottom layer and combine with each other to return the silicon atoms to their normal polarity.
It's quite interesting, Doctor.
Thank you, Brett.
Was that it?
Yes.
Dr. Alexander Edmund Becquerel, you have done it again.
My sincere apologies. I tend to get carried away. Science is my true passion.
Your behavior proves you have learned nothing.
No, not the Arctic Circle, please. Don't do it again.
I think I have a more crafty place to send you this time. Why is it that I cannot get him to stop talking anywhere that I teleport him to?
I don't see why you were so adamant about interrupting him. I mean, you did bring him here after all to teach me. Or, well, and Jamie too, but he's not here. But, and then,
Look, the doctor and I have known each other for a long time. Since 1891 to be specific, and that is 180 years since he was reported to be dead, but like I said, that's a long time. And we've known each other for a long time, and he is an intelligent man, but you give him an opportunity to talk about what he loves, and it is impossible to get him to stop until he either A, runs out of information, which never happens, or B, I just teleport him somewhere else.
alright, yeah, I guess that makes sense. I mean, that also reminds me of you. Alright.
Jamie.
Yeah.
Well, why don't we teleport you back to school? It is getting close to 2:15 anyways.
Okay, I like that.
Brett, you're back! Put me down, you big goof! Oh, I'm glad to see you back, and with all your limbs. MMB, I'm sorry. I didn't mean to be rude. It was a little much, man.
Yes, I'm sorry. I understand that I can be a little much. It's just you guys, you have so much to learn, and I was so excited to teach somebody for once. This might come as news to you two, but I don't have a lot of friends. So it was nice to be able to talk to you guys for so long, especially you, Brett.
But before you go, MMB, we just wanna know, what does MMB stand for?
Oh, MMB? It stands for the Montessori Mythbuster.
That's it?
Pretty much.
Alright.
Well then.
Nice talking to you guys. I'm sure I'll see you sometime in the future.
Maybe so. That was interesting.
Thank God he's gone, though.
You ready for practice?
Yeah, we're gonna be late.
Yep.